Okay, Chapter 2, Section 7, Marginal Analysis in Business and Economics. So, you've signed up for a business calculus class. One of the ways in which this class is different from the standard calculus course is that in this class, on top of the normal mathematical properties and principles, you will also be learning a little bit of economics and a little bit of business verbiage, definitions. The thinking by some is that if we engage students with language from a field that they're interested in, since presumably most of you are business majors, that if we engage you with word problems and language from the world of business, that we will entertain you more and keep you engaged in the material, and the thinking is that you'll do better in the class. I disagree with that logic, but it's not my call. So we got to learn some of this stuff. Okay, all right, so we're going to go through a lot of definitions in this section, and hopefully some of them are already a little bit familiar to you guys. Again, since you're all business majors, you're probably a little familiar with some of this, and some of your other classes you might have heard some of this stuff as well. Okay, a couple definitions. So if X is the number of units of a product produced in some time interval, then C of X is going to be our total cost. Right, so this is a function where we input the number of units to be produced. For example, let's say we make bicycles. So the total cost to produce, I don't know, maybe 10,000 bicycles in 1 week. We would put 10,000 into this equation, and the output would be the total amount of money needed to produce 10,000 bicycles. Right, that's what this equation will give us, right? Okay, and then we'll be introducing marginal cost. The marginal cost is the first derivative of the cost function, right? Remember that little notation means that it's the derivative of the cost function. The marginal cost is the instantaneous rate of change of cost relative to production at a given production level. Okay, so in other words, this equation tells us how much it's going to cost to produce 10,000 bicycles. Maybe, I'm just making up numbers to get a sense of what these formulas tell us. So let's say I want to produce 10,000 bicycles. I'm a big company. I'm making these things. I got to buy the steel. I got to buy some rubber. I got to buy some paint. All kinds of raw materials. I got to pay labor costs. I got to pay the electricity bill for my factory. Several costs. So maybe to produce 10,000 bicycles, it might cost me $1,285,000. Just a random number, don't worry about that. Okay, so now how does this vary? Okay, so the marginal cost will be an equation. So it's not a constant, it's an equation. It's the first derivative of that one. And what happens here is that when you plug in a number, like let's say I plug in 10,000 in here, the output is not going to be the total cost. The output is going to be describing how this is changing at that point. Like if I wanted to go from 10,000 bicycles and I wanted to upgrade it to 10,001, just one extra bicycle, how is my cost function, my total cost function changing? This is an equation that will give me that. When I put in 10,000, it'll tell me how this cost function is changing with one extra unit, right? So it's the instantaneous rate of change of the cost function. That's the marginal cost. Okay, those costs vary from unit to unit. In other words, they're not necessarily linear. So, for example, if I wanted to make just one bicycle, you can imagine it's incredibly expensive to just make one bicycle. There's a lot of costs associated with it. I gotta I got a lot of fixed costs, electricity, I got to buy materials, I got to pay labor, I got so many costs, and I'm just going to make one bicycle. That's very, very, very expensive. On the other hand, if I want to make 1,000,000 bicycles, then you can mass produce them, and there's a lot of savings involved per unit at that point. So the way the total cost function is changing varies greatly based on how many units you're producing. So this output won't be a constant. So let's say, for example, just to make some numbers up, this turns out to be, I don't know, it's 45. What would that mean? It would mean that if I want to change my production level from 10,000 to 10,001, that means that this guy will go up by approximately $45, right? So if I come back up here and plug in the 10,000, I come back up here and I want to plug in 10,001, then my expectation is that the total cost function will then be 1,285,000 and then an extra $45 because of that. Now, I want to be clear, this is just an approximation. This isn't going to be exactly $45 because this is an approximation, right? So it'll be about that. Maybe the real answer, let's remove this. Maybe the real answer is $44.85. We're like, okay, 45 is a pretty good approximation. This $44.85 that it went up, and in fact, your marginal cost, this approximation was 45. So it's a pretty good approximation, but it's not going to be exact. Okay? All right, so next, more definitions. If X is the number of units of production produced in some time interval, then the total revenue is given by capital R of X. Capital R of X is the total revenue for X number of units. So again, sticking with my bicycles, what this tells me is that if I input the number of bicycles, let's stick to 10,000, the total revenue will be the total amount of money collected by selling all 10,000 of them. So, just making up numbers, maybe after I sell all 10,000 of them, maybe my total revenue is $3,492,500. Just a random number I made up, right? Just to have something concrete to look at. If I sell 10,000 bicycles, my total revenue collected is this amount, right? The total amount collected at the register is the revenue. And the marginal revenue is the first derivative of that. So again, if we want to think about what this means, the marginal revenue is the instantaneous rate of change of the revenue relative to the production of the given production level. So we have to think about a production level. So let's say the 10,000. This is going to be some new equation. It's the derivative of that one, but it's some new equation where we input the 10,000. And what this does is it gives me an approximation of how the revenue function, the total revenue function, is changing at that point. So if instead of selling 10,000 bicycles, I sell 10,001 bicycle, then this might give me, and I'm just making things up here, maybe this number is, I don't know, $742. Okay, so this is saying that if I went back to my total revenue function, this one, and I put in 10,001, I'm approximating that my total revenue will go up by this amount because the marginal revenue is that. Now, it's not the exact amount. Remember that this is an approximation. So this would be 3,492,500 plus the 742 would take me to 3,493,242. Okay, and again, this is an approximation to the actual one. We saw in the previous one, in the previous section, that if we want the exact one, we have to think about delta. the delta R is the exact change in revenue. So I calculate the 10,000, there it is. I calculate 10,001, here it is. If I subtract them, I would get the delta value, right? So delta R would in this case be equal to the 3,492,500 minus the 3,493,242, which in this case is actually equal to exactly 742, which means that this wouldn't actually be that. Maybe once I find this this derivative thing, maybe this is equal to 742.53. It's going to be close, but not exact, right? This is an approximation to the delta R, the real change in revenue. Okay, so more definitions. Next, we look at profit. So the total profit is equal to the total revenue collected minus the total cost collected. So P of X is usually what we use to represent the total profit. And then, of course, if we take the first derivative of P of X, that's going to be equivalent to the first derivative of R of X minus the first derivative of C of X. So this gives us the marginal profit. Okay, so the marginal profit is the instantaneous rate of change of profit relative to the production at a given level. Okay, so we input X as the production value, and we get all of these different equations. Let's look at them all together. It's a nice little... Here they are all in one spot. So C of X is the total cost of producing X units. Marginal cost is an equation. It's the first derivative of the cost function. And what it does is it tells us the instantaneous rate of change of the cost function. It gives us an indication of how the cost function is changing at that point, right? What is the cost of the next one from X to the next one? What's the instantaneous rate of change at that point? R of X is the total revenue. Marginal revenue is R prime of X, the first derivative of R of X. So again, marginal revenue is the instantaneous rate of change of the revenue function. How is the revenue function changing at this point? Is the total revenue increasing dramatically? Would making one more push the revenue way up high? Would making one more won't make much of a difference? Maybe that next one plateaus. Or in some cases, making more might actually be detrimental. Like you might make less revenue by selling more units, right? And we'll see situations where that comes into play. It's not true, right? I mean, I think maybe when I first introduced all this, I always thought the more you sell, the more you make, the better it is, always. Make more, sell more, make more money, everything's great. That's not really how it works. There's a lot of reasons for why you might not want to make more. You start losing money. Maybe the cost of making just one more, you think, okay, well, we sold 10,000 bicycles. What's the problem in selling one more? Let's sell one more bicycle. Well, maybe selling one more bicycle means that the company has to buy a whole new batch of steel, like a whole new batch. And so making that one extra bicycle costs them a lot of money. Or it could be that there's some sort of a promotional deal thing that such that the more you sell, the bigger the discount that has to take place. So at some point, the discounts are so big that it starts to hurt your revenue. So there's a whole lot of considerations in the real world. I mean, of course, there's like taxes and like tax incentives, that might benefit or hurt your costs or revenue functions and therefore your profit functions. So don't just take it for granted that the marginal revenue is always increasing. Making one more is always better. That's not true. Sometimes making one more might bring down your revenue. And same thing with cost functions. you instinctually think that producing one more automatically means it's going to cost you more, right? How can it possibly not? But that's also not true. There might be forces at work that such that at some point it might be cheaper. You might actually save money by making more somehow. For example, there might be some sort of a government incentive to help you produce things. So once you make a certain number, like maybe you make 10,000, you don't qualify for the discount. But then if you go past the 10,000, you make 10,001, all of a sudden that triggers some sort of huge government grant. And you're like, oh, that changes everything. So the total cost might actually go down at that point, making one extra one. Stuff like that makes a big difference. I know recently I was reading about Uber drivers. Of course, they get paid by the trip and the mile, but also there's a whole bunch of like incentives to try and get drivers to be motivated to work. So the company will have like little promotions for them. If you get if you complete 10 rides in one day, you get like an extra little bonus. Or if you take somebody more than 2 miles away, like the distance, I don't know, just various little promotions to try and incentivize the drivers to go to areas where they don't normally like to go to. In certain cities, for example, it might be very unpopular to take someone from the airport and go really far away from the city and go like into like a little suburban town far away, because they know that they probably they won't be able to pick somebody up and come back the other way. So there might be little promotions for them to do stuff like that. Anyway, so when you take those kinds of weird promotional things, and then you're thinking about their revenue, the driver's revenue functions, then they get kind of weird things that happen because unusual things get triggered. So my whole point was, don't fall into the mindset of thinking that costs always have to go straight up. Don't fall into the thinking that profits are always in the positive direction, right? That the more you sell, the more you make. That's not true. There's often like a sweet spot, that the perfect number of units to sell is given by the equation. And also keep in mind that in many of these cases, the real world answer is really, really complicated. And all we're doing is we're finding a mathematical equation that does a fairly good job of approximating the real world. So even the equations we're dealing with are just an approximation of the real world, and then often our equation may only be valid for a certain subset of the domain, right? Like this equation does a great job of modeling the total cost of bicycles, but it only works when the inputs are between 10 bicycles and 50,000 bicycles. As long as you do something in there, then it does a good job. For some reason, it's a silly mathematical equation when you put in 2 or 3 or 4. Starting at 10, it starts to do a pretty good job of approximating the real world. And then maybe there's an upper end, right? When you plug in 80,000, 200,000, the math equation that's approximating the real world begins to fail to do a good job of approximating the real world. So we have to keep in mind, very often these equations are not going to be true forever, and they're not an exact translation of the real world. It's an approximation. Okay. So as I was pointing out earlier, marginal means that it's an approximation, right? If you want the real answer, you want that delta, that change in. So if we have a cost function, the cost function is the total cost of producing one more unit, right? So back to the bicycles, I had 10,000 bicycles, and I want to calculate, well, what's it going to cost to do 10,001? What's that change? What's that difference? This is what we would call delta C in this case, right? Remember, delta is this little triangle, and it means change in the cost function. And this is exact. The exact change in the cost function to go from 10,000, so this is 10,000, and then this is going to represent 10,001. That difference there is delta C. However, to approximate this, since this is often too difficult to solve, so in order to approximate this, we use the marginal cost, right? So that's where that C prime comes in. So we find the marginal cost by finding the first derivative of the cost function and plugging in 10,000. This will give me a pretty good estimate to this. And even though it's not exact, we often prefer it because, one, it's easier to calculate, and two, it leads to more things that we can do. We will continue to develop our understanding of derivatives and graphs and interpretations, and we will see that there's a lot of benefits to sticking to this kind of a function. Okay, then revenue. Again, sticking to bicycles. If we had an equation that tells us the total revenue collected, right, we would plug in 10,000 into here, and that would be the total revenue collected when we sell 10,000 bicycles. And if we want to know, well, what's the difference? What if we sold 10,001 bicycles? Then we plugged in 10,000 here, meaning 10,000 plus 1, into the revenue. We subtract the two of these, and this is delta R, the change in revenue, delta R. This is the exact answer. This is the difference in revenue from selling 10,000 or selling 10,001 bicycles. And again, you might be tempted to think, well, aren't bicycles always the same price? Wouldn't it just be a constant change every time? And it might be, depending on depending on the situation. But keep in mind that there's always, in real life, there's always variations. For one thing, there might be promotions, there might be coupons. If you want to sell your bicycle in certain stores, for example, they might demand that you give them a special price. So it might not be as profitable for you to sell your bicycle at a Walmart versus an REI, right? Because the Walmart people demanded that you give it to them at a cheaper price. So you might not be making as much money selling one there. There's coupons. Maybe there's like some sort of a customer appreciation program thing. You might have like a buy two, get one half off kind of deal. And then also, depending on the state you sold it in, there might be different taxes involved. So there's a variety of things that could impact the actual revenue collected when you sell that one extra bicycle. So it's not always necessarily going to be a constant. Okay? And then, of course, just like before, this is often too difficult to find, even though it's exact. And sometimes we like precision. So we often will want the exact answer, which is this. But also, very often, we can settle for a nice approximation, and that's where marginal revenue comes in, which is going to be R prime of X, marginal revenue. Okay, and then finally we had profit. And just like before, if P of X represented the profit function, and then we put in the, sticking to the bicycle idea, if this is going to be 10,000 bicycles are sold, then this output of this function would tell me the total profit collected, right? So it's automatically taking the revenue minus the cost, and then that's where my profit comes in. And then if I want to know, well, what happens if I sell one extra bicycle? What's my profit look like? So that would be plugging in 10,001 and subtracting those two answers. Those two would give you delta P, the change in the profit. Delta P, this would be the exact change in profit if you go from 10,000 to 10,001 bicycles. And again, often we settle for an easier equation, and that would be marginal profit. Marginal profit, which is P of X. Okay, there's a lot of advantages to settling for these derivatives. There's a lot of mathematical properties that come with them. They're easier to find. And then as we develop our understanding of calculus and derivatives and moving forward to integrals and various other things down the pipeline, we will see that there's a lot of advantage to working with these approximations. But, sometimes you want the exact answer down to the penny. What is the change in revenue going from 10,000 to 10,001 units? In those cases where they want the exact answer down to a penny, you want that delta, that change in C, change in R, or change in P, delta C, delta R, or delta P. Okay, moving on. Okay, so let's take a look at this example. A company manufactures fuel tanks for cars. The total weekly cost in dollars of producing X tanks is given by this equation. So it's the cost function. So this is X units, X number of tanks, and the output of this is going to be the total amount of dollars. Okay, find the marginal cost. Find the marginal cost of a production level of 500 tanks per week. Interpret the results of part B. Find the exact cost of producing 501 tanks. So for part A, we want the marginal cost, which is going to be the first derivative of the cost function. So marginal cost is equal to C prime of X, which is the derivative with respect to X of the cost function, which is 12,000 plus 95X minus 0.03X squared. Okay, so that should be fairly easy to calculate. That's going to be the derivative of the first term, which is a constant. Okay, I'll spell it out since we're still getting used to these, but eventually I'll probably skip this step, plus the derivative with respect to x of 95x minus the derivative with respect to x of 0.03x squared. So the marginal cost is equal to 0 from this term. So this is 0. Here we bring out the 95, and the derivative with respect to x of x to the power of 1 is just going to be 1. We can follow our power rule. This is equal to 95 times 1 times x to the 1 minus 1. Okay. Minus 0.03 times 2 times x to the 2 minus 1. Right? Okay, so the first derivative will be equal to, okay, well that's just a 0, I can get rid of it. That's 95, x to the power of 0, 1 minus 1, minus 0.03 times 2, okay, well that's just going to be 0.6, 0.03 times 2 is 0.06, x to the power of 1, x to the power of 1. And now x to the power of 0 is just going to be equal to 1. So we get that our first derivative, our marginal cost, is equal to 95 minus 0.06x. Okay, so what this is, it's an equation where if we input the value c, it will give us the marginal cost of the, it'll give us the instantaneous rate of change of the cost function at the x value. Okay, part B. Find the marginal cost at a production level of 500 tanks. Okay, so part B is super easy. Find the marginal cost at a production level of 500 tanks per week. Part B. Part B, Well, we already have an equation for the marginal costs, right? This is an equation where you input the production level, X, and the output is the marginal cost of production at that level. So we're going to do when X equals to 500, we have C prime of blank equals to 95 minus Z.06 times blank. And so we put 500 into here. And we get that 500 equals to 95 minus 30, or 500 equals 65. Part C, interpret the results of Part B. Okay, so what does this mean? The marginal cost of 500 was 65. So this means that at a production level of 500 tanks per week, the total costs are increasing at a rate of $65 per week. That is the interpretation of this work over here. Okay, so that's how we can interpret this first derivative evaluated at 500. The marginal cost. Marginal cost is at 500 is 65. And this is the interpretation. Okay, part D, find the exact cost of producing the 501st tank. So because we want the exact answer, we know that that means we want delta C. Delta C is the exact change. Delta C is going to be equal to the cost of producing 501 units minus the cost of producing 500 units. Okay, so to get this answer, we're going to take our function and plug in 501, and then take our cost function, plug in 500, subtract the 2. So this will be 12,000 minus. So we're going to get this answer from right in here, and then we're going to subtract. Okay, so we're going to take 501, plug it right into here, and then subtract it from the same equation with 500 in here. Okay, so now we need to figure out what this is. So let's get our calculator and calculate this here. Now we could just multiply 95 times 501 plus 12,000 minus, right? So just calculate it all out, and it wouldn't be that bad here. But we might have a case where we have to calculate lots of them. So we might want to take advantage of our function notation. So turn on your calculator. Go to y equals, and then clear anything you might have on there. Let's type in our equation. So that'll be 12,000 minus, plus 95x minus 0.03x to the power of 2. Okay, so here's my equation. And now if I go to table, we go here and then delete these. Okay, so if you don't know what I'm doing here, I've covered this in a previous video. So hopefully, I think even back in video 1, I did a more detailed explanation of how to do this. So you can go back to 2.1, and somewhere in the middle there, I do a more detailed explanation of this. But hopefully you're familiar with it now. So I know that if I put in a 0, I should get 12,000, right? If I replace x with a 0 there and a 0 there, these two terms cancel, I just get 12,000. So the cost of producing 0 of them is 12,000. And if I put a 1 there, I get approximately that guy there. If I use my arrows, I can get there and get the exact answer, 12,094.97. Okay, so now if I wanted to figure out what is the total cost of producing 500 units. I can put that there. And then again, I can use my arrows and go over there, and then I get the exact answer. Okay, so it's going to be $52,000 to produce 500 units. What about to produce 501? 501 units. Well, looks like that's going to be $52,064.97. Okay, so this guy right here is 52,000, and this guy is 2,000. So we see from our calculator work that this guy right here is going to be 52,064.97, and this guy is exactly 52,000. Okay, so that means that our change in the cost function, the change in C, our exact change, is equal to the difference between 52,064.97 minus 52,000, and so our exact change at that point is the $64.97. Okay, notice that this was a little more work compared to this one. This one was not too bad. We found the derivative, we plugged in 500, things worked out nicely, and we got a 65. And 65 is a very good approximation to this one. The instantaneous rate of change of production at a production level of 500 tanks per week, the total cost is increasing at a rate of $500 per week. It's the instantaneous rate of change of production at a production level of 500 tanks. It's about $65 per week that it's increasing, right? We can see that as an approximation to the cost of increasing from 500 to 501 units. To get the exact answer, we'd have to find this delta C, which we did, and this is just confirming for us that this is a pretty good guess. $65, pretty close to $64.97. All right, let's take a look at a graph of this cost function. So here on Desmos, I created a table where here is the equation of the total cost function. And in this column, I get to put in the production level. So if I put 0, then of course that means we just have 12,000. So that 12,000 can be thought of as a fixed cost. Even if you make 0 tanks, there's going to be some costs associated. Maybe this is the rent for the place, for example. If we produce only 1 tank, then the cost jumps by $94.67. So it looks like that first one costs you an extra. It changes the cost function by $94.97. Okay, so if we start graphing a few of these, so there's a couple dots there, and they're just so close together, it's kind of hard to tell. So let's just jump to a few values. What if we made 100 of them? If we made 100 tanks, it would cost $21,200. If we made 300 of them, it would cost $37,500. Okay, what if we made 400 of them? What if we made 500 of them? What if we made 600 of them? Okay, looks like we just keep going up and up and up and up, right? But don't fall under the misguided idea that cost always goes up, straight up, or anything like that. There are cases when that's no longer the case. So let's keep going up and see what happens. Okay, in this case, they keep going up, 1,300. They keep going up, but it looks like they're starting to plateau. So the total cost begins to grow slower as we make more units, right? That advantage of mass production is kicking in, and it's becoming cheaper to produce extra units. Let's keep going. So maybe at 1500 we reach that level. At 1700, oh, looks like we kind of flattened out, maybe went down a little bit. Let's jump over to say 2400. Oh, 2400 goes way down here. Look at this interesting scenario. This is indicating that if we want to make 2400 tanks, it's going to cost us $67,000. And if we want to make 1700 tanks, less tanks, it costs us more. At this point in production, the total cost of producing them begins to go down. Not just the cost to produce a little extra, the per unit price goes down, the total cost begins to go down. That can be thought of, remember these equations are attempting to explain things in the real world. They are not necessarily exact equations of the phenomena that happens in the real world. They're just attempting to explain it. So what could cause production cost to plummet like this? Why would it be cheaper to make 2400 total cost versus 1700 units? Not just the per unit cost, but the total cost. Maybe think about, like, for example, there could be a tax incentive to produce these tanks. So once you make more than 2,000 tanks, some sort of credit kicks in, and then all of a sudden your total cost goes way down. That could be a case. Or maybe, for example, I was reading that Uber drivers, for example, obviously get paid per trip by the mile, depending on the distance, right? But besides that, in order to motivate their workers and to get them to go to areas where they don't necessarily want to go, or to work during hours where they might not be as popular, that there's little incentives that happen. So if you work from 2 in the morning to 6 in the morning, not that many people want to work during those hours. Not that many drivers want to be out there during those hours available. Even if there's a need, maybe just some of them don't like working between 2 a.m. and 6 a.m. So there might be like an incentive. If you pick up a customer during that time, we'll pay you an extra, $5, like a flat $5 bonus for that fare. Or they might want to incentivize people to, work a certain amount per week. So if you complete 50 rides in 1 week, then you get an automatic bonus of $500 for making that. So if you think about that driver that only did 499 completed trips in 1 week, and they're just one shy and they just don't get it, then they don't get that $500 bonus compared to that other person that gets exactly the 500, and then their income just jumps by that bonus of 500. So for that reason, there's unusual things that happen in the real world. And so when we look at our cost functions, our revenue functions, our profit functions, they might do unusual things. It's not up to us to question why it goes down. We just have to accept it up to a point. Because remember that this equation and all other mathematical equations we use are just an approximation of what happens in the real world. So we might come up with, ordered pairs that describe the exact data. Maybe the exact data is kind of like these jagged little things, but we go, okay, you know what? This other equation kind of smooths it out and gives us a pretty good approximation, so we use it. But that approximation is almost always limited to some domain. There exists some value that just doesn't make sense anymore. Often when you are given these equations, you will be told which domain that function is valid for, or it might be up to you to decide when it stops making sense, when it's no longer reasonable. So following along with this equation, if I keep going and I come up with more dots, 2,600 units at 3,000 units, right? Eventually all these dots will form this curvature, right? So this is the equation, the cost equation that was given to us. And so this is what it looks like. And so we can see that there is a place where the total cost reached a maximum amount. This is the total cost of producing. There's a maximum amount. Looks like it was a little in the neighborhood of 1,500 units. And then the total cost begins to come down. Like I said, there might be weird situations that happen, like tax incentives or weird bonuses or stuff like that. And then down here, there's a place where they even reach zero. According to the total cost function, the total cost of producing 3,288 units is $0. It's free. That's weird. Remember, we're not talking about selling them. This isn't a revenue function. This isn't a profit function. This is just the cost to make them. For some reason, according to this equation, it's free to make 3,288 tanks. It costs you, way up here, it costs you $86,800 to make 1,700 units, but somehow if you jump all the way out to 3,288 units, for some reason that's free. That might not make sense anymore. There might be a reason. Maybe there's some sort of logistical reason for why that is, some sort of a weird, unusual phenomenon that's happening, but it might be the case that this equation stops making sense. It might no longer be valid in that range. So when they give you this equation, they might say this equation works well as long as we have more than 100 units but less than 2,500 units, then it stops making sense. Okay, maybe. Or it might be up to you to decide when it stops making sense, and certainly the places where the total cost function begins to go below zero, that would be a place where we might think, yeah, that doesn't make sense. Because according to this, if we make more, if we make 3,300 units, somehow the total cost function is now negative. How can we interpret negative? It doesn't cost money. You start making money. You start producing money by making it. Remember, again, we're talking about the cost function here, not the revenue function. So how can you be making money by making it? It's weird. But there might be some sort of situation out there where it does make sense. Also, the input values. So remember, this is the number of tanks produced. We can make 500 tanks. We can make 1,000 tanks. But how can we make negative 500 tanks? That doesn't seem to make sense. We're unmaking them or something. So again, it doesn't make sense in the real world. It's up to you to decide when it starts to make sense. So certainly, the input should probably start at 0. And even 0 sometimes doesn't make sense. Maybe you have to start someplace else. Or there might be a case where for some reason negatives do make sense. So it's up to you. But most of the time, we start off at 0 and we go up to some maximum value where the domain is valid. And if it's not given to you, usually the place where it begins to go in toward the negatives begins to be suspect, right? That might not make sense. And often way before that is where we stop. Okay, so now in particular, we were focusing on the marginal cost at 500. So let's come back over here and change these. So when we put in 500, we saw that it costs $52,000 to produce 500 units. And if we put 501, we saw that that jumped to $52,064.97. Okay, these 2 points are so close together that in this picture, they almost look like they're the same point. So I'm going to zoom into here. And here they are. We see that there is, in fact, a distinction between the two. As we saw in the previous, as we just finished seeing, the actual change between the two, that's the $64.97. The actual change, if we take this output minus this output, if we subtract these two, it's the difference is $64.97. On the other hand, if we think about the tangent line at x equals to 500, right? That's this tangent line that comes across this way. The slope of that tangent line is going to be equal to exactly 65, and that's what we think is a pretty good approximation for this value, the $64.97. I'm going to take a picture of this, but I'm going to really exaggerate because otherwise when you zoom in, it's really hard to tell heads or tails of what's happening. So I'm gonna take a picture of this, and I'm gonna exaggerate and pretend this is 500 and that the 501 is like way over here, just so that I can draw it in a better way. Okay, so here's the general function, and like I said, I'm just gonna really exaggerate this guy. So let's say that this is, whoa. So let's say that this is my input of 500. And then, again, I'm just exaggerating it. It's way over here. I'm just going to use this as the input of 501. So that'll jump right over there. So then, therefore, this output 064.97. Whereas this output over here was exactly 52,000. Okay, and also we're going to have this tangent line at this point. So this is going to be the tangent line. Tangent line at x equals to 500. Okay, so now remember that this guy here was c of x, the total cost function, which was equal to 12,000 plus 95x minus 0.03x squared. That was the total cost function. And so we had a couple of points here. What we could do is think about the triangle that's created underneath here. This is going to be delta C, the exact change in the outputs of the total cost function. This is what ended up being exactly the $64.97. It's the difference between these two. It's subtracting these two values, which gives you exactly this amount. Okay. On the other hand, if we calculated the first derivative of the cost function, when we calculated the first derivative of the cost function, we got to this. This is equal to 95 minus 0.06x. Now this is not the red function. The red function is the tangent line, don't confuse it. What this is a function that will give us the slopes of all the tangent ones as we move around. So when we plug in c prime of 500 into this guy, we ended up getting a 65. 65 is the slope of this red line. Slope of the tangent line at x equals to 500. The slope is m. So I'll just put slope equals to 65. And so 65 is the rise over run of the red one, right? Remember slope is rise over run. So that slope is really rise over run of this one. Well, that is going to be a very good approximation to this one. You think about the slope of the red one. Right. To calculate slope, we can always think about a little triangle underneath. We think about slope, we can always think about any 2 points on the line, and we create a little triangle like this. And so the ratio of rise over run will be the slope. So it could be that triangle, and as long as it could be any triangle, let's think about the triangle that goes like this and then comes all the way up to here like this. So we can think about this as the run, and then we can think about this whole thing from here up to there as the run. So if we divide as the rise, so if we think about rise over run ratio of this red one, it's going to be a pretty good approximation to this one. Okay? Like this. Here's one more graphic in general to describe this same situation. We have some sort of cost function here in blue. And so if we want the exact change as the productions go from X units to X plus 1 units, then that change is delta X is 1. So that'll be this gap here from here to here. That gap is delta X equals to 1. In other words, if you just subtract these two things, we get a 1. On the other hand, this represents the output of our function when X equals at a production level X, whereas this height, this output here, represents the total cost of producing X plus 1 units. The difference between the two is this little gap right here, and we get that exact difference by doing this. This is exactly equal to delta C, the exact change in the cost. On the other hand, if we think about the tangent line, that's what this one is, the tangent line there at X, at that point, that tangent line, the slope of that tangent line is going to be calculated exactly by this equation, the C prime of X. So given C of X, we take its derivative, it'll give us this, and this will be a very good approximation. It's going to be giving us this. No, that's it. It'll give us this height there. And as you can see, the green and the yellow are pretty close, especially when we really zoom into a function. So what we want to conclude is this. C prime of X is approximately equal to this. This is the exact change in the cost going from a production level of X to a production level of X plus 1. Whereas we say, well, that's a pretty good approximation. It's approximated pretty well by this derivative. Okay, moving on. Okay, theorem 1. Marginal cost and exact cost. So if C of X is the total cost of producing X items, then the marginal cost function approximates the exact cost of producing the X plus 1 ith item. Okay, so marginal cost is this derivative. We take the total cost function, take its derivative, that'll be this, the marginal cost, and that it is a pretty good approximation to the exact cost, which is the difference between evaluating the cost function at X plus 1 minus evaluating the cost function at X. Okay, so similar statements can be made for total revenue functions and total profit functions. Okay, so finding the exact change in revenue, the exact change in profit involves evaluating those functions at two separate points, at X and X plus 1, subtracting them, you'll get the exact answer. Otherwise, we can just find the marginal revenue, the marginal profit, and in most cases, that'll be a very good approximation. Okay, one more example. So the exact cost of producing the total cost of producing X bicycles is given by this function. Good. Find the exact cost of producing the 121st bicycle. Okay, use the marginal cost to approximate the cost of producing the 121st bicycle. Okay, so for part A, because they say find the exact cost, then we need to find the delta C, change in C, which is going to be equal to C of, and we want to go from 120. We want to go from 121 from 120. Good. So following this little formula, this will be 8,000 plus 230 . Okay, so this is going to be 121 there. This will be 120. This will be 120 there. Okay, so now we just got to crunch that out and get a value. Okay, so to get this, I'm going to use our calculator. Let's go to y equals and type in that equation. Okay, 8,000 plus 230x minus 0.3x squared. Good. Okay, so now go over to table set. So second table set. Make sure that that's under ask. Now we go to table. Okay, and we were interested in 120 and 121. So that's the result for 120 and 121. 121. Okay, if we want the exact answers, we gotta use our arrows to go over and highlight them. And there we go. So $31,437.70 minus 31,280. So it'd be 157.70. Okay, so that's the answer to part A. Part B says use the marginal cost to approximate the cost of producing the 121st bike. Okay, so for part B, we're going to need the marginal cost function, which is going to be found by taking the derivative of the cost function, which is 8,000 plus 230x minus 0.3 x squared. Okay, so we know we can distribute and take the derivative of each one. So the first derivative is 0. The next one we know is going to be equal to 230 minus the last one, which we know should be 0.3 times 2 times x to the power of 1, right? Bring the exponent out in front as a factor, and then subtract 1 from the exponent. And so we get that this formula will be 230 minus 0.6x. And so now we're able to find the results by evaluating this function at 121. So this will be equal to 230 minus 0.6 times that. So we input 121 into this function, and we get we can go over to our calculator and we can type in 230 minus 0.6 times 121, close parentheses, and we get 157.40. Okay, so with a production level of 120, the total cost function is changing at approximately 157.40 So $157.40 at this point. Right? So this is an approximation of how much it would cost to make that next bicycle, to go from 120 to 121. Whereas this is the exact answer. Very, very close. They're only off by 30 cents. Okay, a company's market research department recommends the manufacture and marketing of a new headphone. The research department presents the following price-demand equation. And here it is. The X equals to 12,500 minus 500P, where X is demand at price P. Okay, so lowercase p is the price of these headphones, $70, $100, $200, right? So there is some sort of value per unit, per price of the headphones. That would be this. This would be the price. And based on the price, we could see that X, the demand, the expected demand for these headsets. So, for example, if P was 0, meaning they were free, according to the market research, there would only be 12,500 people interested in these particular headphones. At least that's what the equation indicates. If the price was $1, then we'd get 12,500 minus 500, which is just going to be 12,000. So if the price was $1, then there would be 12,000 units demanded. This could be expected demand per day, per week, right? It's not forever. It's just some expected demand. And so on and so forth. Okay, so we can do some market research to figure out, based on the price, how many people are going to want, how many units are people going to want. And now what we could do is solve for P so that we can find a function of the price as a function of the number of units demanded, X. Okay, so let's just solve for X here. So solve for price as a function of demand. All we have to do is add 500p to both sides. So I'm going to take this equation. All right, X equals to 12,500 minus 500p. Okay, so I'm going to add 500p to both sides. 500p plus 500p. And so I'll end up with X plus 500p equals to 12,500. Next, I'm going to subtract minus x on both sides. And so we get 500p equals to 12,500x. And finally, I get to divide both sides by 500. Divide this side by 500, divide this whole side by 500, and so we'll get P equals to 12,500 divided by 500 minus x divided by 500, which turns into 0.25 minus 0.002x. Okay, so now this is a function, a price as a function of demand, right? So here we input the demand for these headphones, plug it into this formula, and it'll tell me what price that's associated with. Okay, so that's the difference between these two. The way it's written here, we would suggest that the P is the independent variable. Pick a price, and then we plug it in here. We get to figure out the demand at that price point. Whereas if we move it around and solve for P, now X is the independent variable. So if we input the demand at a particular, if we input demand, then this formula will tell us the price associated with that particular demand. Okay, so this is the formula, where X is the number of headphones that retailers are likely to buy at P dollars per set. So that's what this represents. The company's market research department recommends the manufacturer and marketing of a new headphone. Okay, so the finance department provides the cost function. C of x equals to 6,000 plus 3x. So this is where the 6,000 is an estimate of a fixed cost. Think of like rent, for example, that's a fixed cost. And $3 is an estimate of the variable cost per headphone, which is a constant. So this is indicating that it costs the same amount of money to produce one more unit, no matter where you are in the production process. So if you're making 500 headphones, if you're making 501, that cost to go one more headphone is just going to be $3 in this case, right? That's what this cost function is indicating. Okay, so let's solve parts A, B, C, D, E, F, and G. So part A, find the domain of the function defined by the price-demand relationship. Okay, so unless it's otherwise stated, we usually assume that these two values must be bigger than 0. There must be more than 0 demand because negative demand just doesn't really make sense. And also price must be bigger than 0 because otherwise it's like you're buying something, but at the same time they're giving you money to buy it, which can happen in some weird situations, but it's highly unlikely, right? I'm kind of thinking of like extreme couponing people, for example, that have so many great coupons upon coupons and all kinds of stuff that they go to the store, they buy a bunch of stuff, and somehow the store gives them money for taking all their stuff, right? But those are unusual circumstances. Normally, we don't assume that we go into the negatives. Okay, so if we look at this relationship here, we have that x is equal to, that we have p equals to 25 minus 0.002x. We want that to be greater than 0. So we want the price to be greater than 0. So that means that this must be greater than 0. So 25 minus 0.002x must be strictly greater than 0. So if we just add that to both sides, let's add plus 0.002x to both sides. Then we end up with 25 must be strictly greater than 0.002x. Divide both sides by that decimal, 0.002, this side by 0.002. Notice that we're dividing by a positive answer. Therefore, the inequality stays facing the same direction. So now we just need to figure out what this is. 25 divided by 0.002. 25 divided by 0.002 gets me to 12,500. So this is indicating that x must be less than 12,500. I'm just going to flip those around. So this becomes x is less than 12,500. Let's check it. Note that if we let x equal to 12,000, if we let x equal to 12,000 in this equation, then we see that this turns into exactly 0. Okay, and if we go beyond that, then we're going to head into the negatives, right? Because if we let the input value be larger than 12,500, this value would be even larger than 25, which means we go into the negatives. So we're confirming that it's equal to that. So x, the demand for this for these headphones, must be less than 12,500 units. And also we know that x must be greater than 0. So we just toss that in there and say that x must be a value between 0 and 12,500. Okay, so that's the answer to part A. Find the domain of the function defined by the price demand. Part B, find and interpret the marginal cost C prime, okay, so let's go over here, B, C prime of x is equal to the derivative with respect to x of the cost function, which is given by this statement of 6,000 plus 3x. So this is a very easy derivative. We know that the derivative of a constant is 0, and the derivative of 3x is just going to be 3. So that's the answer to part B, that this is the part B. Find and interpret the marginal cost C prime of x. Okay, and so what this means is because it's a constant, it means that the price to produce one more unit is always fixed at $3. Okay, so it's fixed in this little scenario. It's always $3. Part C, find the revenue function as a function of x and find its domain. Well, remember that the revenue function is equal to the total amount of money collected. That's the revenue. Okay, so the function r of x is equal to the number of units sold times the price per unit. Okay, well, the number of units sold, that's the demand for it, right? And that's what x is. So x is exactly equal to this, the number of units sold. We want a function. We want an equation where we input the number of units and the output is the revenue. And now we want a price per unit as a function of x. So price per unit, well, that is exactly equal to P. This is P, the price. That was the original thing that was provided for us. We were told, right up here, that this relationship existed. X is equal to 12,500 minus 500p, where this was the X is the demand at price P. The demand for these headsets or headphones at various price points. So we solved for P and we got this equation. So this is an equation of X. So rather than just putting the price equals to this, I can also rewrite it as a function of x. So P of x is equal to 25 minus 0.002x. Right, that also worked for us if we want to write it as a function. Okay, so this is what I'm going to use. P, the price, is equal to this equation. 25 minus 0.002. So this is where revenue is equal to the number of units sold times the price. And then, well, separate from that, we already have this equation for price as 0.002x. So now we just put that right in there, and we'll have a function for the revenue as a function of x demand. It would be x times 25 minus 0.002x. And so we get r of x is equal to 25x minus 0.002x squared. So here is an equation where we input the number of units demanded, and then this output will tell us the total revenue collected. Right? This is an equation where we input the number of units demanded, and this will output the price associated with that demand. So we put price times units sold, and their product will give us the revenue. Okay, so now let's find the domain I think it asked for, the revenue as a function of x, and find its domain. Well, the domain we said was from 0 for X we said was greater than or equal to 0, but less than or equal to 12,500. Okay, let's graph this and see what it looks like. Okay, so here is our revenue function. Revenue starts off at 0, climbs up. It wouldn't make sense to have negatives, right? So starts off at 0, climbs up to some maximum revenue collected, and then it begins to decline again, and then it goes all the way back down here. And so over here at 12,500, we get back to 0, and beyond that, we start going into the negatives. Okay, so the domain of this revenue function is going to be the same as the domain of the price function. So it's going to be x has to be between 0 and 12,500. Part D, find the marginal revenue at 2,000 units, 5,000 units, 7,000 units, and interpret the results. Okay, so if we want the marginal revenue, we need to find the derivative of this. So D, find the marginal revenue. That means we want to find r prime of x, which we know is the derivative of the revenue function, which is 25x minus 0.002x squared. And so the derivative is equal to 20, well, I'll take the steps this time. 25x minus the derivative with respect to x of 0.002x squared. And the derivative of this function is going to be equal to 25. Following our power property, we bring the 1 out in front, subtract 1 minus 1, we get a 0. So here, just to make sure people are following, this is 1 minus 1, where this is a power of 1 there, minus 0.002 times 2x to the 2 minus 1. So r prime of x is equal to 25x to the power of 0 minus 0.002 times 2 is 0.004 x to the power of 1. That's just going to be a 1. Any time we have a power of 0, that's just equal to 1. So our marginal revenue function is going to be equal to 25 minus 0.004x. Okay, so now that we have the marginal revenue function, let's create a table so that we can solve for the values that they asked for. So let's come over here and create a table. So x, and they asked us to find, let's zoom out a little bit. Part D says find the marginal revenue. We did that. And now we want to find the results at 2,000, 5,000, and 7,000. So when x equals to 2,000, when x equals to 5,000, and when x equals to 7,000. That's what we want. Okay, so here's a little table. We're going to say this is r prime of x. So when x is equal to 2,000, I want to evaluate this at 2,000. So it'll be r prime of Okay, let's use our calculator function. Let's go to y equals clear. And then our function is just going to be 25 minus 0.004x. So 25 minus 0.004x. There's our equation. Let's go to our table, second table. And now I can just input these values to get my results. So if I input 2,000, 2,000, I get 17. If I put 5,000, 1, 2, 3, I get 5. And if I input 7,000, I get negative 3. So 17, 5, negative 3. So remember that this is describing the instantaneous rate of change of our total revenue function at various points. So when the production level is at 2,000 units, the revenue function is increasing by $17 per unit. At a production level of 2,000 units, the total revenue is increasing at a rate of $17 per unit. Okay. Next, at a production level of 5,000 units, the total revenue is increasing at a rate of $5 per unit. Okay. And then finally, at a production rate of 7,000 units, the total revenue is decreasing because it's negative. At a rate of $3 per unit. Okay, part E, graph the cost function and the revenue functions in the same coordinate system. Find the intersect points of these two graphs and interpret the results. Okay, so let's graph them with technology. So let's go to Desmos and graph them both. So we already had the revenue function, r of x equals to this. Here's our revenue function. And now let's graph our cost function. Okay, so here is our revenue function from before. That's right here in blue. And now if we draw our cost function on our same grid, we get this. And a couple of important things that we can get out of this. For one thing, as long as our revenue quantity is higher than our cost value, our costs at a particular production point, we're going to be making money, right? The difference between the two is the profit. So, for example, if we let A equal to 3,000 here, at 3,000, if the production level is 3,000, this is our cost function. It would cost $15,000 to produce 3,000 units, but our total revenue collected would be 57,000. So the difference between the two would be our profit. So as long as the blue is above the green, as long as our revenue is above our cost, we will be gaining profit. Notice that what we would like to do to optimize this is usually to maximize profit. So we would be looking for the place where the gap is the biggest. That's what we'd be interested in finding. If we keep going with production and we make more units and more units, more units, eventually the gap between the two gets smaller and smaller and smaller until they get to this point where they're equal to each other. So here is a place where they intersect. Or over here, another place where they intersect. So at approximately 279 or 280 units, the cost function and the revenue function will be equal to each other. They both will equal the same amount. Therefore, the profit will be 0. And over here, at approximately 10,720 units, 20 units, 21 units, somewhere around there, the cost function and the revenue function will also be equal to each other. Therefore, again, the profit will be 0 at this point and at this point, right? At these two production levels, the profit will be 0. Okay. What we normally want to do is optimize profit, so we want the biggest gap to generate it, and we can kind of ballpark where it would be, maybe a little higher. You see, like right around there, we get to the 0 point. This is too small, so we can kind of ballpark approximately where the highest point would be. Maybe somewhere around there is where profit would be maximized. And we know that if we go past a certain production point, here profit's getting smaller, the gap is getting smaller, profit's getting smaller until we get to the point where they're, 0, and then they swap around. And then from that point forward, at a production level of 11,800, this is indicating that the costs are higher than the revenue collected, so we are losing money here, right? Normally, we'd like to avoid that. So in general, this is a nice graphic to describe the relationship that exists. We have some sort of a revenue function. That's the blue one. That's this blue one here. The blue one is the revenue function. And then going across this way is this one, which is the cost function in green. They intersect at 2 points. Right? The gap between them is the profit. As long as the revenue function is higher than the cost function, that's profit. On the other hand, the place where the cost function is higher than the revenue function, that represents a loss. That's when we're losing money. Okay? The point where these two graphs intersect, those points right there are called the break-even points. We use Desmos to find those 2 points, but that won't always be an option for us. So we got to find a way to figure out when they equal each other, right? So that's where we begin. Set both functions equal to each other and solve for x. X being the number of units produced and sold per week. Okay, so let's do that now. So to find the break-even points, the places where the revenue function and the cost function intersect, set them equal to each other and solve. We saw from before that our revenue function was actually equal to 25x minus 0.002x squared. And we saw that our cost function was equal to 6,000 plus 3x. So all we have to do is bring everything to one side and then solve it. So if I bring these on the left over to the right by adding plus 0.002x squared to both sides, plus 0.002x squared to this side, and then also subtracting 25x from this side and subtracting 25x from this side, we get the following. On the left-hand side, we're going to get 0 equals to, I'm going to write down the 0.002x squared, and then 3 minus 25 is going to be minus 22x plus 6,000. Okay, this is a quadratic, right? It's not going to factor nicely at all. So why don't we just jump right into our quadratic formula? Remember that quadratic formula states that given some quadratic in the form of ax squared plus b plus bx plus c, then equals to 0, then the solution to this is going to be x equals to negative b plus or minus the square root of b squared minus 4ac all over 2a, the quadratic formula. So in our case, by our problem, that means that the role of a is being played by 0.002. The role of b is being played by this negative 22. Don't forget the sign. And finally, the role of a is being played by 6,000. Okay, so all we have to do is plug into this formula and find our results. So we get negative well, let's see. Negative 22 plus or minus the square root of negative 22 minus 4 blank 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 all over 2 times blank. So the b is negative 22. So that goes there and that goes there. And then the a is 0.002, and then this is 0.002. And finally, the c is 6,000. So 6,000 goes in there. Okay, so just use your calculator to crunch this out, and you should hopefully get something like this. Equals to positive 22 plus or minus the square root of so that should lead to two different answers. X equals to 22 plus 20.880613 divided by 0.004. And then the other answer, or x equals to 22 minus 20.880613, the whole thing divided by 0.004. And so in this case, we should get that x equals to 10,720.15. So somewhere between, here we're going to have to round to whole numbers, so somewhere between 10,720 or 10,721, somewhere in that production level we get to 0, right? So at one of these 2 points we're going to get that break-even point, and then the other one comes from here. And so here x equals to 279.8467, or again, somewhere around 279 or 280. Somewhere between these whole numbers, again, we get a break-even point. Let's confirm that again with Desmos. So with Desmos, it was easy. We clicked that guy right there, and we got the 279.8. So somewhere between 279 and 280 whole units, or if they want you to give you a decimal value, that's fine. That would be the low end. That's a break-even point. That's a place where the revenue function equals the cost function. The revenue of producing these number of units will equal the cost of producing these number of units. And then over here is the other one at 10,720.1. So somewhere between 10,720 and 10,721 units will be a place where the cost of producing that many units is equal to the revenue collected. And in fact, Desmos does also gives us the actual value. So that's what this output value is. At 279 units, it looks like both the revenue and the cost are about $6,839. And so they both equal each other. Therefore, the difference between the two is 0. Therefore, the profit is 0 at that point. And over here at 10,720 units, it looks like the cost and the revenue collected are both the same at about $38,160.46. Again, this will be a place where profit will be 0 because the cost to produce is equal to the revenue collected. Okay, so set the revenue function equal to the cost function, move everything to one side, set equal to 0. In this case, luckily, we ended up with a quadratic, so we can use the quadratic formula to solve for our answer. And then back to this general grid. So back to this one, we found these two break-even points, right? So one of them is here. We found that one of those break-even points was at 279 units. And then the other break-even point is over here somewhere at the 10,720. So in terms of making a profit, you'd want to stay somewhere in this sweet spot. Make more than 279 units, but less than 10,720. In this range, you're in the money. You're making money. Of course, you might want to further specialize that and figure out exactly where you make the most amount of money. But as long as you're somewhere in there, you're making money. Okay? When you make more than that, more units than that, you're going to start to lose money. When you manufacture less than that number of units, you're losing money. Okay, hope that's clear now. Find the profit function and its domain and sketch the graph of the function. Okay, so the profit function is equal to the revenue minus the cost. Well, we already have a revenue function and we have a cost function, so if we just subtract them, we'll get to our profit function. So part F is find the profit function. So P of X is going to be equal to the revenue function, which was 25x minus 0.002 x squared, that's the revenue, minus the cost, and the cost was 6,000 plus 3x. Be careful with the sign because it needs to be distributed. So the profit function is equal to 25x minus 3x when I distribute there. And then it'll be minus 0.002x squared minus 6,000, which simplifies into negative 0.002x squared plus 22x minus 6,000. Okay, so here's our profit function, and let's graph it. Again, let's use Desmos to graph the whole thing. Okay, let's take a look at these graphs. So first of all, we already had a revenue function. That's what this blue one is, right? Total revenue collected. The green one was our cost function, total cost to produce these items. So if I wanted to find the profit, it would be the difference between the two. So for example, let's say I keep track of that. Let's say what this means is that if I produce 7,000 units, it will cost me $27,000 to produce 7,000 units, but my revenue collected will be $77,000. So at this point, my profit is going to be $50,000, right? The gap between these two is $50,000. So that should be a point on my profit function. So let's say I come over here and I put $7,000 into this table value. This table over here is generating profit based on the equation we just found. So I'm just going to use it to confirm that that's in fact the equation I want. And let's put it in purple. Let's go with purple. Okay, so we have one point that belongs in our profit function. Okay, it's that gap between these two. We have another couple of easy points because we already discovered that if we come over here at this production level of 10, well, it's kind of hard to land on it here, but it's at 10,720. At 10,720, we already know when we're at 10,720, we know that that should be a 0. So when we go over to our profit generating function, if we put 10,720-ish, it's pretty close to 0. There was actually a decimal in there somewhere, right? So I think it was like 0.1, like that. It's really close to 0. 0.15. Okay, so there's another dot in my profit function. At this point, the output should be 0 because the profit is 0. Also, we found that way over here, there was another point where the profit should have been 0. At 279-ish, we should also have about a 0. So if we go over our profit function and we type in 279, we should have something else that's pretty close to it. It's like around 279 to 280. We get another point where the profit should be 0. Okay, so let's find a few other values. So if we keep track about that gap that exists between the revenue and the cost function, right? If I keep track of that orange line and I keep measuring it, let's find a couple more. So at 2,000 units produced, there is $11,937 is the cost to produce. Okay, so let's get a couple of other values. At 2,000 units, it costs $12,000 to produce 12,000 units, but the revenue is 42,000. So there should be a profit of 30,000. Let's put that into our table over here. So when we're producing 2,000 units, we get a total profit of 30,000. That's what this means right here. So we have another point on our profit function. If we keep going and we find other points, how about 3,000? How about 2,500? How about 9,000? Right? We keep finding all these points, right? What do these little dots represent? This height right here, this output represents the gap between that exists at that point, right? So if I scoot this over to 9,000, there, then that gap is equal to 30,000. You see how the gap between the two is 30,000? Let's try 10,000. At 10,000, we have this point right there. That means that the gap will be 14,000. The profits generated when we produce 10,000 units should be $14,000, which means that this gap that exists between those two should be this distance there should be 14,000, and it is. It costs $36,000 to produce 10,000 units, and it costs we collect $50,000 in revenue when we sell 10,000 units. So that gap equals that. Okay, so if I continue to come up with some more values, let's say 4,000, 3 at 5,000. Eventually, we start to see that this forms this sort of a shape, okay, a parabola. And that's in fact exactly what we get when we graph, when I type in the equation for the profit function. Eventually, all those purple dots form that solid shape, and then that becomes the graph of our profit function. Notice that the profit function has domains starting there at 280, sort of where we got our 0, and over here in the neighborhood of 10,720, where we got our other 0, approximately. Okay, so we found this, and we know that the profit will be positive on the set. So we can say that P of X is greater than 0 as long as X is greater than 280 but less than 10,720, right? Around there. Okay, did we answer the question? Let's see, what was part F? F said find the profit function and its domain, sketch the graph of the function. Okay. So the domain is, the profit is allowed to go negative. That doesn't, it makes sense in the real world that you would go into the negatives. So this is not the domain. I'm just indicating when this thing is going to stay positive. But the domain is still related back to the x. So the domain of the profit function is still when x is greater than 0, but x is less than 12,500. That was what we had before. That was the domain of the cost function, the revenue function. So that is the domain of the profit function. Okay, and finally, man, this has been a very long problem. Find the marginal profit at these points. The marginal profit, okay, that's easy. Luckily, the marginal profit is going to come from taking the derivative of this function and then evaluating it at those points. So G, find the marginal profit. That's going to be P prime of X, which is equal to the derivative with respect to X of the profit function, negative 0.002 X squared plus 22X minus 6,000. So P prime of X is going to be equal to negative 0.002 times 2, the power of X, the power of 1, right? Bring the 2 out in front, subtract 1 from the exponent, plus 22, so bring the 1 out in front. 1 times 22 is 22. And then subtract 1 from the exponent, which means it's 0, which means it's a 1. And then the derivative of the constant is 0, so this is going to be it. Profit function is going to be negative 0.004x plus 22. And then they asked us to evaluate this at a few points. So let's create a table. So for 1,000, we just put 1,000 in here. For 4,000, we put 4,000 in here, and 4,000 in here. And for 6,000, we put 6,000 in here, and 6,000 in there. Okay, so let's calculate each one of these. Okay, and let's interpret these. So this is at production level of 1,000. Okay, at the production level of 1,000 units, at that point in the production process, the profit is increasing at a rate of $18 per unit. So as long as the rate of the profit is positive, it's paying off to make more, right? You're headed in the positive direction. Okay, at the production level of 4,000 units, the profit is increasing at a rate of $6 per unit. So you're still heading up. It still makes sense to make even more units. You're still increasing your profit, but it's slowing down. You used to be increasing your profit by $18 per unit, and now you're only increasing it by $6 per unit. It's still good. It's still better than not making any more units, but you're slowing down. The growth of your profit is growing down per unit at this point. And finally, at a production level of 6,000 units, the profit is decreasing at a rate of $2 per unit. So now you're in the wrong direction. Making more units is actually decreasing your profit. If that's all you're interested in, the profit, you might want to stop making more units, right? You'd be better off if you stop making more units because your profit is on its way down. It's decreasing at a rate of $2 per unit at this production level of 6,000. Okay, I know that was a really, really long problem, and it's probably very easy to get lost in it. I wish that I had a way to kind of put the entire thing all in one big screen so you can kind of see it from start to end, but that's not going to happen. So let me just quickly flow through the various questions, and hopefully that is enough to help you see the big picture. Okay, so here's where we started. We were given this equation that represented the demand for a particular headphone as a function of the price. So we kind of go out with marketing and figure out, we ask surveys and ask people if they're interested in this headphone at a particular price, and we can kind of figure out this equation, right? This relationship that exists between the number of units desired and the price point. So we can go in either direction. We solved it for P, so that way we can write it down as a function of X. P as a function of price, where P is the price. It's not the profit, don't confuse it. So that would have been a source of confusion here, right? This is lowercase p for price. rather than capital P for profit. So that hopefully that doesn't confuse you too much. So this is price. Based on X demand, right? So the demand and the price relationship is given by this one. Okay, so we solved all of these questions here. So here's our answer to part A, part B. Part C said find the revenue function. Right, so here's part C, part D. Here's F and G, and there were some cool graphs along the way as well. So a very long problem. Okay, so your book has one that's similar to this if you want to look there and see if you can follow. Hopefully what I've done here will at least help you follow what's in the book, but that takes like 2 pages in the book as well. So it's a long, long problem. All right, let's move on. Okay, more definitions. If X is the number of units of a product produced in some time interval, then the cost per unit, the average cost, is equal to this little formula. What we do is we take the cost function, C of X, and divide it by X number of units. That'll give us the average cost. And we identify it by putting this little bar over C of X to indicate that this is the average cost. Okay. On the other hand, the marginal average cost is given by the first derivative of the average cost. So first find the average cost function and then take the derivative of it. Okay, that'll be the marginal average cost. More definitions. If X is the number of units produced in some time interval, then the average revenue is equal to the revenue divided by the number of units. Right? So that will give us the average revenue. This R of X gives you the total revenue collected for X units produced. And if we divide them, we get that average revenue, which is indicated by this little bar on top, the average revenue. And then, of course, we have the marginal average revenue, which is going to be the first derivative of that function. The derivative of the average revenue function will be the marginal average revenue function. Okay. And finally, of course, we have profit. If X is the number of units of a product produced in some time interval, then we have the average profit indicated by this equation. It'll be P of X, the profit of the profit function, as a function of X units divided by X, and then that's again indicated by that little bar. So that little bar in math often indicates average. So and then, of course, then the marginal average profit is the first derivative of the average profit function. Okay, so let's put them all together in one big happy box. Right, so average cost, find the cost function divided by X. That'll be your average cost function. When you want to find the marginal average cost, step 1 will be to find this function, find the average cost function, then take its derivative. Okay. The average revenue will be found this way. Find the revenue function divided by X. That'll be the average revenue. And then to find the marginal average revenue, take the derivative of that function. So it's important to do it in that order. Right? Very often you'll just be asked, find the marginal average profit function. Okay, the first thing, though, is to find the average profit function. Take the total profit function divided by X. That's the average profit function. And then take its derivative, right? It's important to do it in that order. Okay, so for example, the total costs of printing X dictionaries is given by this equation. So the cost function is here. They ask us to find the average cost and then the marginal average cost. Marginal average cost. And then evaluate those two at 10. And then use the results in part B to estimate the average cost per Bible at a production level of 11 bits per day. Okay, so this is going to be easy compared to that huge problem we just did. Okay, we have the cost function. So the average cost function is just equal to the cost function divided by X. So in fact, it usually Well, I wouldn't say it makes things easier, but okay, so we get that. So this is the average cost function. Okay, well, this is going to be 2,000 plus 10x minus 0.2 x squared, and then all we have to do is divide that by x. Okay, so then this becomes, okay, so we know we can separate this into 2,000 divided by x plus 10x over x minus 0.2x squared over x. And now these x's cancel, and this one reduces. So we're left with x bar x equals to 2,000 times 1 over x, writing it like that, plus 10 minus 0.2x to the power of 1. Squeeze this over here. Which means that average cost function is equal to 2,000, and I'm going to rewrite that using a negative 1 in the exponent for this guy, plus 10 minus 0.2x to the power of 1, or just leave it as x. Okay, that's a great way to leave it so that I can take its derivative, right? So they also wanted us to find the marginal average cost, so that would be c bar prime of x. Take the derivative of that. That'll be the derivative with respect to x of the cost function, of the average cost function. So c bar prime of x, the marginal average cost function, right? That's how you can read this. Start there and say marginal cost. Marginal average cost function is equal to the derivative with respect to x of 2,000 x to the negative 1 plus 10 minus 0.2x. So I'll take this one at a time here. This is going to be equal to 2,000 times negative 1 times x to the minus 1 minus 1. Right? That's how we use the power rule here. And then plus 0, and then plus 0 minus, and then this is just going to be 0.2, and we know that we bring down the 1, we put a 1 minus 1 in the exponent, so we know that that's just going to be that constant. Okay, so marginal average cost function equals this, so the marginal average cost function equals to negative 2,000 x to the minus 2 minus 0.2, which we can simplify a little bit more as negative 2,000 divided by x squared minus 0.2. Okay, so we found our equations. Part A, find the average cost function, find the marginal average cost function. We got them, so this is the answer to part A. Let's see, this is probably the best way to find that one, and then this one. Okay, so now that we have those two, part B said evaluate both of those when x equals to 10 and interpret the quantities. So evaluate these when x equals to 10. So the average cost function is equal to 2,000 over x. That's this part. I'm putting the x back underneath the function, the 2,000, plus 10 minus 0.2 times x. Oh, let's put a blank there. Let's come back over here and put a blank there. And so we're going to evaluate this one. That's a 10, that's a 10, and that's a 10. So we get the average cost is going to be equal to, canceling 1, that's going to be 200 plus 10 minus 2. So that would be average cost, and we have 10 is equal to 208. On the other hand, C prime of x, the marginal average cost function evaluated at 10 is going to be equal to negative 2,000 divided by blank squared minus 0.2. And so we're going to input a 10 into here. 10, 10. 10 squared is 100. So that would be 100. I'll just copy it down. This is equal to 2,000 divided by 100 minus 0.2. Marginal average cost function at a production level of 10. And now two of those zeros cancel, right? It's a nice little trick. So we're left with just minus 20. So it's minus 20 minus 0.2. That's going to be deeper into the negatives, negative 20.2. Okay, so here's our answer for part B. When x is equal to 10, then this is our average cost, and this is our marginal average cost. Okay, at a production level of at a production level of 10 dictionaries per day, the average cost of producing each dictionary is $208. This average price per dictionary is decreasing at a rate of $20.20 per dictionary at this production rate of 10. So I was being a little wordy here, but just highlighting that this number and this number, both of those are only valid at this production rate, at this point in the production process of 10 dictionaries per day. This decreasing, and of course I put the word decreasing here, meaning that it is negative. So negative 20 is indicating how the average per unit price is decreasing at this production point of 10. So for part C, use the results of B to estimate the average cost per dictionary at a production level of 11 dictionaries per day. What's going to happen when we go to the next dictionary? Well, that's exactly what this is attempting to tell us. This is an approximation, but we're pretty sure that when we make 11, the average cost per dictionary is going to be 208 minus the 20. Okay, at a production level of 11 dictionaries, we estimate the average cost per dictionary to be $187.80. And we got that by focusing on our production levels of 10 dictionaries. We got that the average cost for 10 dictionaries was $208 per dictionary at this production level. But we saw that the marginal average cost was negative 20. So we're expecting, as an estimate, it's not an exact answer, but we estimate that if we subtract 208 minus 20.20, we'll get to this number, and that's how much we expect will be a pretty good approximation for the average production cost of 11 dictionaries. Okay, so I know these have been some very long, complicated word problems. So hopefully I've done enough to help you get through the homework. Please try it out and let me know if you have any questions, problems, or issues.